So in the previous lecture we have discussed about how to calculate the total heat in and total heat out in the bottom section. So this amount, when we add all these values, that is basically the heat in that comes out to be this value. And when we are going to add all these three values, one is missing here, W is missing, that is our objective basically, that is related with the heat out. So how to find out this missing value, that is the QW? It's very simple, because we assume that heat in is equal to heat out. So amount of this QW can be easily calculated by just minus 386,106 minus 119,011, this value. When you minus it, you will find the value of QW. Now this is the in fact value of QW. So QW is calculated. We know that QW is nothing but the mass flow rate multiplied by the enthalpy. So mass flow rate is known, this is mass flow rate. So mass flow rate is known. How we can find the HW? HW is simply find out by divided the mass flow rate. And if we divide the mass flow rate, we can get HW, that is about 396.6. so this is value is calculated for H value. So enthalpy is calculated in the reverse order. Now there is a new term, delta H, delta enthalpy. What is the meaning of delta enthalpy? Let us come to the next slide to understand it. So for that thing, W, that is the bottom, this is the bottom, but this bottom is coming from the flash zone. So at the flash zone, the portion at the bottom that have the HW value is 420, and if you go and you can see at that temperature, the enthalpy of the W, that is the feed portion in the, when it is in the flash zone, is 420 BTU, and when it is at the bottom section, the value is 396. Just now we have calculated this value. So the difference between these two values, 420 and 396, this difference is known as a delta H value, and that comes out to be 23.4. so this is the value that we have calculated. We want to do it. So now the next step, as you can see here, so delta H we have calculated in this way. CP is given value, so 0.64, it is a given value. And then this is important thing, how to calculate the delta T value. So now let us look about the delta T value. We have discussed all these things. Now come to the system. If in a system, for example, just imagine you have only the bottom residue, and in the system at the bottom residue is at temperature of flash zone, and there is a heat removal from the through the system from the bottom, and now it is now at temperature T1. So there will be a difference. We know about MCP delta T example. So we know about MCP delta T. We can find out the amount of energy that is leaving from the stream 1 to stream 2. We can find out because there is a release of the temperature drop. So according to temperature drop, MCP delta T gives about the amount of energy, and that is equivalent to the m dot delta HW, means delta H of the bottom. So delta HW, this is a one term. We have calculated this delta HW. This is the delta HW, that is 23.4, and CP is given. So we can calculate the delta T. So delta T is nothing but delta H divided by CP value. So this CP value is given, delta H is given. If you divide delta H by CP, we can get the delta T calculated. So delta T calculated can be find out by this expression, delta H upon CP. Now our final stage, we have to check this is delta H calculated, and we have already assumed the delta T calculated, and we have already assumed the delta T as 30 degrees Celsius. So we have to compare it, and if delta T calculated is equal to the delta T assumed, okay, our objective is achieved. There is no further iterations is required, and if it is not, then we have to go for the second iterations. In our case, we have assumed delta T as 30 degree Fahrenheit. Our calculated delta T is 36 degree Fahrenheit. So, and this is the ratio 1.2 is the ratio, and if suppose this is, we can tolerate this difference. If I say that in the calculations you can go up to the 40 plus minus 6 plus minus 5 and 6 degrees Celsius. So it's okay. Now our objective is achieved, and if we say that no, you have to reach up to the 30, then you have to repeat this step again by taking the next assumption. That can be a 36, that can be a 34, not exactly the same, maybe sometimes. So iterations, you have to repeat iterations again and again until unless you can find out the your calculated value is equal to the assumed value. So in this way we have to find how to find the bottom temperatures. In this way we have calculated everything. So flash zone temperature is given 645, that is given, and similarly this is the temperature that we have calculated 615, because the temperature difference between these two is 30 value. So because we have assumed that one and our assumptions is correct, and the vapor that is leaving from the flash, basically from the bottom section, this vapor is at temperature about 640 degrees Celsius, and this is all about, we know that this is given 500. So overall our ultimate target, that is 615, that is achieved. So this is all about the bottom calculations. So thank you very much.